The Earth's magnetism, or terrestrial magnetism. In 1600, William Gilbert, who was a physician to Queen Elizabeth I of England, showed that the force acting on a suspended magnet is not due to the influence of the pole star, but to a magnetic field which is present all over the surface of the Earth, as if the Earth was magnetized. Gilbert made a large spherical ball from magnetite, the poles of which were situated on two opposite ends. By placing a small magnetic compass on this magnetite sphere, Gilbert showed that the compass took up a definite direction at different points on the sphere as it does in the case of the Earth. According to his view, the magnetic field on the surface of the Earth can be approximately represented as if caused by a huge imaginary bar magnet in the interior of the Earth, but inclined to the geographic north and south axis of the Earth. This concept of terrestrial magnetism has been illustrated as shown in figure. The north end of the imaginary magnet has a south polarity, while the south end possesses the north polarity. Declination. In order to understand the term declination, let us first define two terms: geographic meridian and magnetic meridian. Geographic meridian at any place is a vertical plane passing through the geographic north and south poles of the Earth. Magnetic meridian at any place is a vertical plane passing through the magnetic north and south poles of the Earth. The angle between the magnetic meridian and the geographic meridian at a place is known as declination or variation. In figure ABCD is the magnetic meridian, and AB-C-D- represents the geographic meridian at a place. The angle BAB- is equal to theta is the angle of declination. The angle of declination varies from place to place on the Earth's surface. Gilbert believed that the declination at any one place was constant in time, but this belief was soon proved wrong. There were several periodic variations in the value of declination for a given location. Dip. A magnetic dipole suspends freely at its center of gravity so that it can rotate about a horizontal axis. Suppose dipole takes up the position as shown in figure. The angle through which the end pole dips down with reference to horizontal is called the angle of dip. It varies over the Earth's surface. The places where the dip is 90 degrees north pole down and 90 degrees south pole down are called the magnetic poles of the Earth, generally denoted as NM and SM. Along a line called the magnetic equator, which runs somewhere near the equator, the dip is zero. Horizontal component of Earth's magnetic field. The total intensity of the Earth's magnetic field does not lie in any horizontal plane. Instead, it lies along a direction making an angle delta, angle of dip, to the horizontal. The intensity B bar of the Earth's magnetic field can be resolved into two rectangular components. 1. The component in the horizontal plane is called the horizontal component BH, or simply H. 2. The component in the vertical plane is called the vertical component BV, or simply V. As is clear from figure, tan delta is equal to BV by BH. Cos delta is equal to h by b. Sine delta is equal to v by b. Now, cos square delta plus sine square delta is equal to h square by b square plus v square by b square, or 1 is equal to h square plus v square by b square, or b is equal to square root of h square plus v square.